Hi, and welcome to 7.3 Modeling Data Using Exponential Functions, otherwise known as exponential regressions. What I would suggest is that you watch, follow along, see how I go around about using the online tools, and then you do the first example yourself. After watching the video. And if you're feeling stuck, come back to the video to kind of help you get unstuck. So this is the example on the first page that says the population of Manitoba is given from the years 1951 to 2011. So I've got a data table and I'm putting in my X values separated by a space here. So this is the PlanetCalc.com /5992. You can see that's a link on Schoology. But this is the online tool that we'll use on our phones and computers to do the regression. So we're typing in the X values separated by spaces. We're typing in the Y values separated by spaces. And what those numbers mean is those are showing the population, not 776 people, but 776,000 people. So it's really important to keep in mind, sort of the units that we're talking about. So looking at the table, you can see the word population, and then in brackets it says thousands. So this is 776,000 people that were within Manitoba in 1951. And each one of the X values has to correlate with a Y value, so it has to be sort of 1-to-1. Now you will sort of move on to the next section. You can leave these on if you'd like, but I prefer that they be off so that I only see the one that I'm working on. And also, typically, I think this starts at 4 digits after the decimal point. You might not see all the digits you need. So it's a good idea to open it up to 20 just so that you can see all the, the whole mitt full of digits, because sometimes we're looking at scientific notation to represent the numbers. So just double check, click calculate, and they're going to give you a scatter plot. So they're going to be plotting these blue dots are X and Y values. The yellow line is the approximation of the function of best fit. So in this case, it's showing us an exponential function. And, it looks pretty close. These dots that are far away, they're not too far away. So how far off are they? We want to look at the correlation coefficient, and we see that it's 0.975. That's pretty good. Remember, a correlation coefficient of 1, this is also called the R-squared, but if R-squared or chi-squared or correlation coefficient is 1, then you've got a perfect fit. So this is saying, wow, like that yellow line is pretty close to showing what those blue dots are showing. So this then is our function of best fit, or the function that models the data. This little guy here, this little dot, it's not a decimal in the sense that it's down at the bottom of the line. It's sort of in the middle. That's representing a multiplication sign. So our function's in the form of AB, where A is your coefficient, and B is the base. So this is the base, and then that's the exponent working on it. So this is representing a multiply sign in between. If you're working on your phone, I think you got to get out a pen and copy these numbers down. But otherwise, for those of you guys on computers, you could just Control-C to copy that up and over to your metacalculator. So we're on metacalculator, graphing calculator, on equations. I just pasted in there. I'm going to be super accurate, super precise with my approximation because I've got all those decimals there. It's going to be amazing. I like to, sorry, just a few. So I pasted it all in there. I like to change that little dot into the asterisk, so it's the star, Shift 8, that will be representing our multiply sign. And also I need to go back to the end and make sure that this is saying to the power of x, not a multiply by x or like where it's beside it. So the way to tell the computer like, hey, this is to the power of x is Shift 6. This little symbol is called a caret, and yeah, it looks like a little hat, but that's Shift 6. So it'll know it's 1.07 to the power of x. On this guy here, you should see plot graph. If it didn't already plot, or sometimes when you press enter, you're going to get it there. But we can see our graph, and we can zoom in or zoom out. So if you're in a position where you've looked and your graph looks like this, keep zooming out until you can actually see it. So, and then you can move the space around. On table, this is where we can go in for, let's say, question C, where it asks, what's the population in 2020? We can go into table, say, yes, give me this equation or this function as a table, and then just change one of the x values to 2020, because the x values are our years. And what that's telling us is that for the population in the year 2020, it's estimating it at 1,349,000. So keep that in mind. Yeah, the Y value is 1,349.5, but that's meaning thousands. So overall, this actually represents 1,349,000. So in D, the next step is to estimate when a population might reach 1.5 million. So it would be awesome if we could type in here, but unfortunately we can't. That would be cool to type 1500 here and then it tell us what Y is. Unfortunately, we have to go out. We need to make a new equation where Y is equal to 1500. So this is this blue line that's coming across here. So Y is equal to 1,500, 1,500 thousands, meaning 1.5 million, and we go to intersection. So plot the line, go to intersection, plot the points of intersection, yes, and now it's telling us right there, we can't see it, move it. Whoa. Let's plot that point again. Now this is pretty close. I know it's not exactly 1,500, but it's like really close. So what we could say is in 2034, almost 2035. In almost 2035, it'll be, 1.5 million, or at the end of 2034 would be what we could say. So that's your regression. We do the regression itself using PlanetCalc to find the formula or to find the function, and then we use our meta calculator in order to extrapolate different features of the function. Good luck.